Welcome to the deep dive. You sent us a really fascinating stack of articles this time, all about a pretty rare event back in April 2025.
That's right. We're talking about Uranus passing in front of a distant star.
Exactly. That enigmatic ice giant. And, well, it wasn't just a quick flicker, was it? It sounds like it was a huge opportunity for scientists. Once in decades chance, really.
Oh, absolutely. It's called a stellar occultation. Basically, Uranus, in its slow orbit, it just momentarily blocked the light from a star about, 400 light years away.
Right.
And the way that starlight dimmed and then brightened again as it sort of grazed through Uranus's atmosphere, it acted like a natural probe.
A probe. Okay.
Giving us incredibly detailed information, stuff we couldn't easily get otherwise,
Right.
Especially for a planet so far out. It's been a long, long time since we had a chance like this for such an in-depth look.
Yeah, I bet. So for you wanting that quick but thorough understanding of this event, well, that's exactly what this deep dive is for. Let's dig into what happened on April 7th. Uranus moved directly between us, here on Earth, and that star. Sounds simple, I guess, but the implications are pretty big.
It is simple, in concept.
Yeah.
But the beauty is really in the details of that moving between.
Okay.
As Uranus's atmosphere started to block the star, it subtly bent the starlight first.
Ah, refraction.
Exactly. So the star seemed to dim a little before it vanished completely, and then it brightened again as Uranus moved past. Scientists were meticulously recording this whole fluctuation.
And that gives them the light curve.
Precisely.
Yeah.
The light curve. And it's not just, a line on a graph. It's basically a treasure map of Uranus's atmosphere. Different altitudes, different properties.
And this light curve is the absolute key, isn't it? I saw that quote from William Saunders at NASA Langley.
Oh, yeah.
He said, by observing the occultation from many large telescopes, we are able to measure the light curve and determine Uranus's atmospheric properties at many altitude layers. It's like the atmosphere left its fingerprint on the starlight.
That's a great way to put it. A fingerprint. Think of that curve as a vertical slice, cutting right down through Uranus's atmosphere. The way the light dips and recovers tells us about temperature, pressure, density, all at different heights, especially in the stratosphere.
Stratosphere, that's the middle layer.
Yeah, that stable middle layer. Above all the clouds and weather in the troposphere. Understanding the stratosphere, well, it's vital for figuring out Uranus's long-term climate and, for planning any future missions we might send its way.
Right, gotta know what you're flying into.
Totally. And what was really fascinating, actually, were these little wobbles they saw in the light curve.
Wobbles?
Yeah, subtle ones. They hinted that the temperature up there isn't just a smooth change with altitude. It seems to have these surprising peaks and valleys. That's a big clue for understanding its whole energy balance, which has been a bit of a puzzle.
Wow. It really is like unlocking secrets written in starlight. And this wasn't just like one person in their backyard, right? This was a huge operation.
Oh, absolutely massive.
Yeah.
NASA Langley coordinated it. We're talking over 30 astronomers using, I think, 18 different professional observatories spread all over the globe.
18. Wow.
Yeah. Saunders mentioned it, too. He said, this was the first time we have collaborated on this scale for an occultation. It just shows how significant this event really was for everyone studying planets.
Makes sense.
And different teams had slightly different goals, Some were tracking how energy moves around in the atmosphere.
Oh, okay.
Others were trying to figure out why its upper layers are so hot, which is still a bit weird.
Uh-huh.
And some were looking at the rings. Uranus has faint rings, too, or atmospheric turbulence, or even just trying to nail down its orbit more precisely.
And the lead investigator for NASA was Kunio Sayanagi.
That's right, Kunio Sayanagi.
Yeah.
It's pretty amazing to think about all these scientists, different countries, different time zones, all working together virtually while this, cosmic shadow play unfolded.
Yeah, it really shows how science works these days. Interconnected.
Definitely. And speaking of nailing down the orbit, that's actually a bigger challenge than you might think.
Really? We don't know exactly where it is.
Well, we have a good idea, of course. Voyager 2 gave us that amazing flyby in '86.
Right, the classic pictures.
Yeah. And the last really bright occultation like this was way back in 1996. So since then, Uranus has trundled quite a way around the sun. Our knowledge of its exact position, it's only accurate to within about maybe 100 miles.
100 miles. That sounds like a lot when you're trying to aim a telescope at a tiny star behind it.
Exactly. In space terms, it's enough uncertainty to make pointing tricky. So this new data is gold for refining its orbital path. Really crucial for planning future observations.
And you mentioned 18 observatories. Were there some key players?
Yeah, definitely some big ones involved. NASA's own infrared telescope facility, the IRTF, That's up on Mauna Kea in Hawaii.
Oh, okay.
Emma Dahl from Caltech was there. And then you had the McDonald Observatory in Texas, their Otto Struve telescope. William Saunders and Erica Cook were there gathering data.
And Emma Dahl made an interesting point, didn't she, about why gas and ice giants are so useful to study.
She did. Because they don't have a solid surface, right? They're like these giant natural atmospheric labs.
Less complicated than Earth's atmosphere in some ways.
In some ways, yeah. You can study things like cloud formation, wind patterns, atmospheric waves, without the interference of mountains or oceans. So, for instance, during the occultation, a really sharp dip in the light might mean a dense layer, or maybe even the edge of a ring, whereas a more gradual dimming might suggest just a smoother change in the atmosphere's density. It's all in the details of that light curve.
Like reading atmospheric tea leaves, but with starlight. And they actually practiced for this, didn't they? A kind of test run.
They did, yeah. Smart move. Back in November 2024, there was another occultation, a dimmer star, though.
Oh.
And it was only visible from parts of Asia. So telescopes in Japan and Thailand observed it. It was basically a full dress rehearsal, let them calibrate everything, test their data collection, make sure the whole multi-observatory coordination would actually work for the main event in April.
Like a sound check before the big concert.
Exactly like that. And that practice run turned out to be incredibly valuable. Some researchers from the Parrots Observatory and the Space Science Institute, they observed that November one from India.
Right.
And their observations were pivotal. They let the teams massively improve the predictions for April 7th.
How much better?
They nailed down the timing to the second, and they updated Uranus's predicted position by about 125 miles.
Wow. From 2 billion miles away. That's incredible precision.
Isn't it? It just shows the power of combining observations, collaborating like that.
So let's talk about Uranus itself for a second. We hear Jupiter and Saturn called gas giants. Uranus is an ice giant. What's the key difference?
Good question. It's still mostly hydrogen and helium in its atmosphere, like Jupiter and Saturn. But deep inside, instead of metallic hydrogen like the gas giants have, Uranus has this sort of hot, dense, slushy mixture.
Slushy.
Yeah, water, ammonia, methane, stuff that we'd call ice out there in the cold. But under the intense pressure inside Uranus, they're more like weird fluids. That's the ice in ice giant. And it lacks a true solid surface.
Gotcha. And the rings. People always think of Saturn.
Right. But Uranus has rings too. 13 known ones, actually. They're much darker and fainter than Saturn's, mostly ice and dust. It's a common mistake to think Saturn's the only one.
Huh.
And these occultations, they're great for studying the rings, too. Quick flickers in the starlight as a ring passes in front can reveal details about their structure, find new features maybe, map them out better than we could before.
So this April event gave us this amazing snapshot. What's next? Can we do this again soon?
Well, Uranus will pass in front of a few other stars over the next 6 years or so, but they're dimmer stars.
So harder to get good data.
Probably less detailed, yeah. Still useful, but maybe not quite the gold mine this last one was. Looking further ahead, though, NASA's really got its eye on 2031.
What happens then?
Another bright stellar occultation by Uranus is predicted. And the hope for that one is to use airborne observatories, like Sophia used to be, or maybe even space telescopes.
Get above Earth's blurry atmosphere.
Exactly. That would allow for even more precise measurements, much cleaner data. So yeah, it's exciting to think about what we might learn then.
Okay, so let's wrap up this deep dive. It seems clear this stellar occultation back in April 2025 was, well, absolutely crucial. A detailed look at Uranus we just haven't had in decades.
For sure.
And thanks to this event, this huge global effort, we've learned a lot more about its stratosphere, its atmosphere, got a better fix on its orbit, and even more about those faint rings.
Absolutely. It's really quite remarkable how much information, how many insights we could pull from that single, relatively brief alignment. It really makes you think, doesn't it? About just the vastness out there and all the secrets still hiding in these distant worlds.
Definitely.
And considering how much we learned from just this one event, I mean, what other unexpected discoveries might be waiting for us as we keep getting better at looking, finding new ways to observe Uranus, other planets, maybe even worlds beyond our solar system? Well, it's a pretty thrilling thought to ponder, you know? What else is out there?